Hello, this is Caleb Unger and Nick Losee with presentation 5 on chapter 4, which deals with generation of variates from standard distributions. It's kind of piggybacking off of the last chapter of how to generate random variates. So just a recap, we covered variate generation in the last chapter, and you generate random variables by sampling according to their distribution. And you can see kind of the steps or the way we break it down right here as a chapter 3 recap and how to generate random variates. So the first part of this chapter deals with the standard normal distribution, and we know the function is as follows. As you can see on the screen, it's a function of z, which would be the variable we're interested in, and it's on the support from negative infinity to infinity. And anything is pretty much a function of mu, which is our mean and our standard deviation, theta, and that would be multiplied times our z value. So therefore, after integrating, and we find the CDF to be the integration from negative infinity to z of our function. And our function, or our PDF, is as follows: 1 over 2 pi theta, the exponential raised to basically the z-score over 2, which you can see on there on the slide. So therefore we can see that when we're generating variates, they're going to fall under the distribution that has the mean of mu and the variance of theta squared. It's going to be the standard normal distribution. So then it goes on to cover the Box-Mueller method, and the reason that we use this method is because it's simple and fast. And so the way they initially derive this formula is by taking two standard normal random variables, x1 and x2, following a very similar distribution to what we just looked at, the double normal, with e raised to the very similar exponential function with both of the variables squared over 2, with 2 pi now is not under a radical since we're dealing with two of those random variables. But the whole thing with Box-Mueller is we have to transform these variables into polar coordinates like we were taught in calculus, which you can see here. So then we convert that to the new density that we would have, the new density function, which you can see as follows, which is basically taking the Jacobian with respect to each of the variables in dr and d theta, which would give you this function as you see on the screen. And the support here now is from 0 to infinity and 0 to 2 pi for the radius and for theta, our angle. So now we have to invert both of these variables to continue doing the Box-Mueller method. So after we find those variables, we solve, and we see that they're independently distributed, as 1/2 r squared is very lines up with the exponential, and then theta is a element of the uniform distribution from 0 to 2 pi. So we're going to use two random numbers, y1 and y2, as I have put on there, and invert the CDFs very much like before in order to obtain our random variates using the Box-Mueller method. And when we do that, you can see we get the results on the screen for theta and r equaling square root of -2 times the natural log of our random variable 1, and theta being 2 pi times the random variable that we generated for the second one. But if we transform this back into our x variables, we get the following. As you can see at the bottom of the screen, a function of cosine and sine for our respective variables, and using our random generated variables. However, the reason we don't always use this is because sometimes it's hard to generate the tails on the distribution, so there is another alternative to the Box-Mueller method, since it's already an alternative method, and we take two variables u and v that compose the unit circle. And so then we find out very quickly that if we take the inverse tangent of v over u, then we're getting another aspect or another uniform distribution from 0 to 2 pi, and u squared plus v squared being on the interval of 0 to 1, which kind of bounds our our distribution now. So then we can set these variables much like we set r and theta 1 to 2 pi y, our second random variable, and u squared plus v squared equaling our first random variable. And so plugging these in, we would get the following on the screen, which is much more usable in its format.
Now we're going to take a look at an improved envelope rejection method. Now typically we're folding the standard normal distribution in half, where we want to majorize the h function and choose the optimal values of c and lambda. We perform this by looking at h of x and g of x, looking at g of x over h of x, and then our objective functions become minimizing c plus 1 over lambda and maximizing the value of lambda. Because we require that g majorizes h such that lambda and c are chosen properly, we take a look at the probability of acceptance. We can see that this is an improved envelope rejection method because the probability of acceptance for your values is higher. It's a 0.88623. And this is an improved method as opposed to just setting c and lambda equal to certain values, such as in the butcher method. Because we require Now that we know we have a higher acceptance rate for the variate generation, let's take a look at how we accept or reject the random value. So the prospective variate is generated by inverting the CDF function for R1 we have the following for x. If R is in certain brackets, then we give the value of x a certain function. Then we give R2, given R2, we accept or reject based on the following. And if that value of x is less than or greater than the value of c. Under special circumstances, we can determine that the value generated is inconclusive. And this is only if the expectation is within certain parameters and if the random number is within certain parameters. In that example, the variate generation, the function is squeezed between 1 over R2 minus 1 and 1 minus R2. Now we're going to take a look at the log normal distribution. So this is a much used distribution in that example, the variate generation, the function is squeezed between 1 over R2 minus 1 and 1 minus R2. Now we're going to take a look at the log normal distribution. So this is a much used distribution. Knowing the values of the expectation and the standard deviation of y helps determine the probability density function, and then you can derive the formula for plugging in random numbers. You would then plug in random numbers. Knowing the values of the expectation and the standard deviation of y helps determine the probability density function, and then you can derive the formula for plugging in random numbers. You would then plug in random numbers.